9.3 is what's considered reactivity or the reactivity series for redox reactions. It is going through and identifying which elements are more willing to give up or take electrons and therefore are more willing to be reduced and or oxidized, and knowing if a reaction is actually going to move forward or no reaction is going to occur. We're going to look at the metals first. The more reactive the metals, the stronger reducing agents they are. Remember from 9.2, a reducing agent means that the element's going to be oxidized, but it's going to force the other compound to become reduced. So if it's a stronger reducing agent, it is easier to oxidize that element, which means that element is more willing to lose their electrons. This is tested by reacting two metals together and seeing if there's a change that occurs. And we tend to see that change in the formation of a precipitate in a single replacement reaction. There are three different types of reactions you can run. You can run a reaction with an acid, with water, or single replacement. And IB tends to focus on the single replacement because then we can solidly identify if there is a precipitate that occurs. Here is an example. We have zinc that reacts with copper sulfate. The products are copper and zinc sulfate. And in this reaction, you see in the products with copper and zinc sulfate that we would have a copper sulfate actually come out as a solid. So as you can see here, zinc was originally a solid, now it's in a compound. Copper was in a compound, and now it's a solid, so precipitated out through this reaction. We therefore can look at the metals as that is what's being oxidized and reduced, and we have our ionic equation. So we see that we have zinc and we have copper 2+. After that reaction, we have zinc 2+ and then just copper. So you could go through and assign the oxidation values. So if we have a 0 there, +2, +2, and 0, you can see that a redox reaction occurred, and therefore a precipitate was formed. Now, the question is, how do we know that this reaction would have moved forward? And that is what the reactivity series is all about. The reactivity series is a series that we use to predict if redox reactions will occur between a metal and the ion of another metal, as we saw in the previous example, where we had a pure zinc reacting with the ion of copper. Ion then became a precipitate, a solid out, and zinc became that ion. In order to know if this is going to occur, you have to understand who's the stronger reducing agent, and therefore who becomes readily oxidized. Here's a series. We go from magnesium to aluminum to zinc to iron to lead to copper to silver. I apologize, there's no good way to understand why it's in this order without understanding the standard electrode potentials, which is what we will be getting into in 19.1. So at this point, this is pure memorization. Magnesium is our strongest reducing agent, which means it readily oxidizes. Therefore, it's the one that's going to react the most out of the entire series. Silver is the weakest reducing agent, therefore it's the least readily oxidized, and will not actually become a pure ion. It would not react unless it was with a stronger atom. Let's look at some examples of what this would be. All right, so the first example, we have zinc chloride, and we are reacting it with 2 silver. Because zinc is already in its ion form, so I'm just going to write zinc in its ion form, and it's reacting with silver. Now, the question is, does silver have the capability to cause zinc to take electrons back? Is silver the stronger reducing agent? Going back to our reactivity series, no, silver is at the very bottom. Therefore, silver is not able to push its electrons away onto zinc. That being said, no reaction would actually occur here. In the next reaction, we have iron and we have magnesium. So does magnesium have the power in which to give its electrons to another metal? Go to the reactivity series and you see that magnesium is at the top, iron is below it. Therefore, magnesium is the stronger reducing agent. Therefore, it oxidizes easily, meaning it's going to shove its electrons onto iron, causing a reaction to move forward. So we're going to get magnesium chloride, and iron is going to precipitate out. And of course, you have your balanced reaction. Therefore, now magnesium is in its ion form, and iron has gone back to its solid standard state. And that is how you have to go through and figure out if a reaction is going to occur. And we'll go more in detail with this in 19.1. Again, it comes down to straight up memorization. What about nonmetals? So the more reactive nonmetals are stronger oxidizing agents, so the opposite of metals. Therefore, they are more easily reduced. Therefore, they want to take or gain electrons more readily and most willing in which to take them. Think about the trend in electron affinity, the willingness to take on electrons during a transition. The reactivity series for nonmetals is a lot more straightforward than it is for metals, because with metals you have not only your representative metals, but you have transition metals, and you have all those different ionization energies and the different ions. If you're working with Fe+3, Fe+2, there's a lot of stuff that's going on with metals. Non-metals, it's very straightforward. And we focus mainly on the halogens. You saw this back in topic 3 when you looked at the chemical properties of your halogens, and we're actually coming back to that. The reactivity series for our nonmetals then, therefore, goes from F2 to Cl2 to Br2 to I2. So our strongest oxidizing agent is fluorine, which means it's the most readily reduced, which makes sense because it has an electronegativity value of 4.0. It really wants those electrons, therefore it's going to be the most prominent in accepting them. Iodine, due to its large size, is the weakest oxidizing agent present. Now, how do we know that a reaction will take place? What's beautiful about the halogens is you will see a change of color when they're doing a reaction. So if you see yellow, that's going to be your fluorine. A yellowish green color is going to be chlorine. A red-brown color is bromine, and black is iodine. So if you see a change in color, you know that a reaction has taken place. So let's look at 2 examples of what this would be. Here we have chlorine is reacting with potassium iodide. So iodine is in its ion form. We want to look at who wants to become reduced more, or is therefore the stronger oxidizing agent. Chlorine is above iodine, and therefore wants to be reduced a lot more, and will oxidize iodine. Therefore, you are going to get potassium chloride and iodine as your products. And of course, go through and balance them. Now, chlorine has become the ion of choice, essentially. What does this mean in terms of color? In the other solution, if we're pumping chlorine in, chlorine has I'm going to switch colors here, has a yellow-greenish color. So we'd expect this beginning solution to have a yellow-green color to it. If a reaction was to move forward, this color is going to change, and it does move forward. Iodine comes out of solution, or comes out of the ion form, and iodine is black. So you should see a change from yellow-green to black, and you know that iodine has come out of solution. Looking at the next series, we have chlorine is reacting with potassium fluoride. So that means we're working with a fluorine ion. We need to identify if chlorine has the power to oxidize fluorine. Well, fluorine is above chlorine, and therefore no reaction is going to take place. Again, we know we're working with chlorine, and so we're going to start with a yellow-green solution. And it's not going to change. We're not going to see a change in color. Therefore, we'll know visually that no reaction has taken place.